Welcome everyone. In today's class, we are going to take a example C code and we will try to see how we can design a efficient hardware using high level synthesis from that input C code. Okay. So, what we are going to take is merge sort, and merge sort is something is very common, everybody knows. So, I took a example which is something everybody understand, and then we will try to first I just try to explain what is merge sort, and then how that algorithm works, and then I will talk about the high level synthesis of merge sort. Okay. So, if you already know that merge sort is a stable sorting algorithm. So, it is given a set of numbers, it can be integer or floating point, does not matter, set of numbers, and then you basically sort them in ascending order, right. So, and we usually apply merge sort, which is developed by John von Neumann in 1945, which is kind of a divide and conquer algorithm. Okay. So, the first thing is it is basically how the algorithm works. Let me try to explain. So, basically we divide the big array into always half, right. So, we have divide by 2 basically. So, we have the big array, we divide it by 2, and then again I will keep dividing the by 2 and so on, right. So, that means I have log n step until I reach a unit size array, right. So, first suppose if you think about a array size of 8, the width is 8. So, I just divide into 2 arrays, right. So, this is my divide part, right. So, there is a divide part going on, and then I have 2 arrays, and then I am going to take this array and again I am going to divide into 2, right. So, and I will take this array, I will again divide into 2, right. This is how the algorithm works. Then I will take this array, I will divide into 2. So, so now it is becoming unit size array, right. So, then I am going to take this, I will divide it into by 2, and then I will take this array, I will divide into 2, and I will take this, I will divide into 2. So, this process will go on until individual array size become 1, right. So, this is my divide approach, and then I am going to conquer, right. So, I am going to merge it. So, once we reach this individual array level, I can assume that this is already sorted array of 1 elements, right. So, this is a sorted array of 1 elements. So, I am going to merge this 2 sorted array into another one. So, the problem here is that I have given 2 sorted array and I have to merge them into a single sorted array, right. So, what is happening in this direction? So, I take this array and this array, I will have these are the 2 sorted array, I am going to merge them into a sorted array like this. Then I am going to take this and this, I am going to merge them and I am going to get this, right. So, similarly, I am going to take these 2 sorted array. You can understand they are actually 2 consecutive sorted array, but the index is very much interesting. So, if I start from say location say I1, I have a sorted array of width size say 4. So, this is the, so it depends on the which level you are doing the merging, and then this is my I2, and the next array start from I2 plus 1, and it goes say some I3, again this width is basically width, right. So, this is how merging happen. So, so this is also width. So, the basic idea of merging is that we have 2 sorted array and they are actually consecutive, and we have to merge this 2 sorted array into another sorted array of size which is double of this 2 size, right. So, basically it is a summation of these 2 size, and if you look into the problem. So, if I start as for location I1, and if the width of this sorted array is width, then this index is I2 is nothing but I1 plus width minus 1, this is my width, and this and the next location, the next array start from I2 plus 1, right. So, which is nothing but I1 plus width, right, and this is still I3. So, I3 is nothing but basically this I1 plus 2 into width minus 1, right. So, this is how this happened. So, basically if you understand here is that once I take these 2 array, I just sort them into this, I take these 2 array, I sort this into this and so on, and then I am going to take these 2 array of size 2, I am going to create a sorted array of size 4, right. Similarly, I am going to take these 2 sorted array of size 2, I am going to create a sorted array of size 4, and then in the last step when my width become 4, I will take 2 array of size 4 and I am going to create a sorted array of size 8, right. So, then I am going to get a sorted array. So, this is the whole process, and this is the and this is how this merging happens. So, suppose I have given two sorted array. So, this is one sorted array, this is one sorted array. You remember this is basically nothing. So, this is basically my in one, right. So, this is my in one array, the way it is written here, and this is my in two array. And how the merging happens? So, basically I will maintain a pointer the current point, because these are all sorted arrays. So, what I should do, I just compare these two element, and whichever is the smaller one, I am going to copy that into my output array, right. So, among 3 and 1, 1 is smaller. So, I just put it 1 into the sorted array, and then I am going to increase this pointer from 1 to 2, right. So, this is where I am going to do, and this since this array is still my pointer will be at the location 3. Now, I am going to compare 3 and 2, and I found that, so this means this part is already sorted. So, 2 is smaller. So, I am going to copy 2 into my sorted array next location, and I increase the pointer. So, my current pointer will be here, and it will be still hit here. So, now I am going to compare 3 and 5, and I found 3 is smaller. So, I will copy 3 into the output array in the next location, and I will increase the pointer here, right. So, the every iterations I will basically take the current locations of two arrays, compare which number is smaller. I am going to copy that particular element into the output array and increase that pointer by 1, right. So, this process will go on, and at some point of time what is going to happen, it might happen that one array is finished, that all the elements of one array is copied, then the rest of the elements of the other will be copied one by one, right. So, that is all. So, this is overall merge sort, everybody aware, but I just for recapitulations of the things I just explain, right. And this is there in any data structure books, that merge sort algorithm. So, this is my that divide process, that the way I do, basically I always find out the mid, which is basically L plus R by 2, and then what I do, I just do the merge sorting for the same array. So, from L to M, right. So, initially I call this merge sort from index L to R, right. So, initially I will just call from 0 to n minus 1, right, if the size of the array is n, and then I am going to take the middle, and I will call this for left part of the array, and then this is for the right part of the array, and this is a recursive call, right. So, basically you can understand that if you just do this, so it will recursively break this part only, right. So, because if you take this, so it will break this, then from it will be called for this, then it will break like this, then it will be called for this, it will break like this, and then it will call for this. Once this is done, then it will be called recursion call, come back to this, then it will break this, then recursion come back again, it will break this, then recursion come back, and then start to working on this part, right. This is how the recursion will happen. And then once I, so these two process will make sure that I will still I reach all the individual array at this level, then this recursion will happen, I mean stop, and then this tail recursion part, that merge part is going to happen, right. So, then now the merging will happen recursively, because I have so many calls. So, automatically so many merge will happen. So, finally, the first iteration this level of merge will happen, then the merge of 2 will happen, then merge of 4 will happen, and so on, right. So, this is how the whole thing will work, right. So, these are all we are aware of, and then this merge function is basically whatever I just explained in this diagram. So, this particular algorithm is written here, right. So, here to make it a little bit generic, I just put a data type is D type, which is basically can be integer, float, anything, right. So, this is my size, and this is the first index, that the way I talked about. So, basically this is my I1, and as I mentioned, so basically I am going to take a array like this. So, this is my I2, and I3 is given by this I3, right. So, this is also with, this is also with. So, from these 3 pointers I can understand the start location of the first array and start location of the second array, right. That is what is happening here, that my start location of second array is F2, because that is I2, this is the start location of the second array, and this is basically I2 minus 1 is the end location of the first array, right. So, the both ways. So, the earlier I just talked about this is I2, but you can consider the start location of the second array also R2, it is a similar thing, right. So, we need basically 3 pointer, not 4 pointers, because this I2 and I2 minus 1 is basically we can manage from this I2, okay. And then this is the I3 is the last location. So, what is happening here, you can understand, this is my the loop that I talked about in iteration. Ideally I am checking whether this element is less than this, then I am copying this the element of the first array in output array, and I increase the pointer, otherwise I just copy the element of the second array and increase the second pointer. So, this part of the code makes sure that if one array is completed, it will copy the other part of the other array directly, right. So, that is actually ensured by these two lines. Okay. So, this is the overall algorithm, and once this is done, this out is the output array, right, and ideally I should copy this out to the original array, because if I want to sort the array into the same place, so I need to copy this output array into input array, right. So, that is all. So, so the first thing is that suppose so you get this code, you have written this code, right, for merge sort, and now try to do the high level synthesis for this. What is the first problem you are going to face? The first problem you are going to face is the recursion, right. If you remember that high level synthesis does not support these recursions, right. So, if you try to synthesize this code using high level synthesis, it will say that I can't handle this recursion. So, I am not able to generate a hardware from this, right. So, this although this is the right version of the merge sort algorithm, you will not get able to generate a hardware from this because of the recursion. So, what is the option? So, you have to make a iterative version of the merge sort, and which is not very difficult. So, we can write that. So, I am not going to change this function will remain as it is. So, I have to write a iterative version of this algorithm, okay. And this is this. So, the idea here is to explain this. So, I do not have any recursion, you see here there is no recursion. So, I just replace by 2 for loop, right. And what is the idea? If you remember that finally that recursion what it does is basically break the whole thing till the size width is 1, right. So, what is happening here? So, I will just maintain outer loop which is called stage. So, it is basically the divide is this loop will take care of that. So, basically the divide is a trivial task. You can assume that basically what is happening, I am going to have the array. First I am actually merging the individual array into 2 and then individual array into 2, then I am taking 2 consecutive array size of 2, merging into a and create a sorted array of size 4, and again I am going to take this, I am going to create this, and from this 2 size 4 I am going to create 8, right. So, this outer loop is basically is that stage. What is happening here is it just assume that my width is 1 initially, right. So, it basically maintain the width is 1, then 2, then 4, then 8, it is basically 2 to the power I, because it is a double. So, by 2 is happening, right. So, basically this outer loop, the stage loop will basically will give you the size width. So, when width is 1, I am going to take 2 array size of 1 and I am going to merge them into 1, right. So, that process is happening here, right. So, what is happening here is that whenever my width is 1, so how many merging is going to happen? I am going to take this 2 array. So, for this 2 array I have to decide what is my I1, this what is my I2 and what is my I3. So, that calculation is happening here, and then I am going to call the merge, right. And after merging the result is going to store in array temp, okay. And then see, so when is width is 1, so how many times, if the array size is 8, how many times is going to happen? This loop will go for 4 times, because it is 2 into width, right. So, basically it merge this 2, then you will take this 2, then it will take this 2, then this 2, right. So, the inner loop is going to do that. Then once this is done, so I have a sorted array like this. So, where every 2 individual element is sorted, then my width become 2 into width. So, now I am going to take the width 2, and then again this this loop will be called. Now, this loop will again decide that this I1, I2, I3, these 3 index for these 2 array first, right. So, it will take this array. So, this will be my I1, this will be my I2 and this will be my I3, and it will call this. After this sorting is done and this sorted array is generated, it will now start, it will create, this is my I1, this is my I2 and this is my I3, again it will sort, right. So, so since this is 8 array, so this loop will go for 2 times, then this width will become 4, right. So, once this width is 4, this this loop will go for 1 iteration. So, it will just decide this is my I1, this is my I2 and this is my I3, and it will just do the sorting and it will call the merge to do that. So, this is my iterative version of the algorithm, and I think it is very much clear. And then once everything is done, as I mentioned, the temp is my sorted array, I should copy to the original array, right. So, I am just copying the data to that, because that is the array I want to sort. So, this is there. So, this function with my this merge function. So, if I take this merge function and this merge sort array, and then if I ask high level synthesis to synthesize, it will be able to do a synthesis, right. It will be able to give you a RTL, right. So, what I am going to ask you, you just do that, right. So, you take these two version of the code and you synthesize it using any high level synthesis tool, specifically Vivado HLS, what we will going to take in this particular course. So, we will get a basic implementation, right, and we will see what is the latency of the design and what is the area, what is the performance, what is the clock you can achieve. So, you just try to measure that. Okay. So, here you can actually fix the size, because once you run something you can fix to size. So, any size. So, the example I have shown for 8, but you can actually create to any size. So, but when you synthesize, you have to specify the size, because dynamic array is not supported, right. So, you cannot have a hardware which can execute size 4, size 8 and all, right. So, it has to say this is the array, sorted array, this hardware can handle a array of say 16 or say 32 or 20, whatever it is. So, it is only going to handle that size. Okay. So, you will generate the RTL. Next, as a developer, what you want to achieve? So, the base level may not meet your target, right. So, I want to create efficient hardware. So, that will be my objective, and now I am going to try to develop a efficient hardware for this merge sort. So, I have created a version of the algorithm which is synthesizable first of all. The initial version was not synthesizable. So, I do some modification, I make it synthesizable and I get a hardware, basic hardware, and which is obviously not the efficient one. So, the next things what we have to think of, we have to apply the tool features, optimization features, and since we can see here there is a loop. So, effectively you can see here there is a for loop here, there is a for loop here, and this merge is also there is a for loop, right. So, there is a 3 nested for loops are there. So, and there is a array, right. So, this temp a or array. So, obviously the optimizations of the tool that will be relevant for this is unroll, loop pipeline and array partitioning, right. So, what I am going to suggest is you should actually apply this loop unroll, loop pipeline and also array partitioning in different combinations. Okay. So, and see what is how the performance is varying, right. So, this is what is called design space exploration, right. So, basically you can apply this unroll, you can apply pipeline. So, if you ideally you know that if I unroll, my area will blow up, because there is no loop, it will create this many copies, but it will run faster, my time to execute the things will reduce, right. So, earlier if the loop execute for 3 times 10 times, and if I unroll, probably it might take 1 or 2 clock to complete it, right. Ideally can 1, but because of some dependencies might take 2-3 clocks. So, the design will be faster, but area overhead will be more, and the pipeline is something is kind of a trade off, right. So, where the area overhead is not that significant, because you have to just add some pipeline stage, and probably you cannot share some of the resource because of the stages happening independently. But because with the pipeline I can actually execute the multiple iterations of the loop in parallel in pipeline manner, my performance usually is order of n of the number of iterations, right. So, that we already know that. So, what I will strongly recommend you, just you take this 2 version of the code, you try to apply this unroll, pipeline and array partitioning and see how the performance is varying, and what is the particular scenario where you get the best performance in terms of time, what is the best area optimized design, and what is the trade off, right. So, what is the combinations where you actually get the area overhead is not that much, but performance is also significantly improved. So, this is what you should actually do once you use high level synthesis to develop a efficient hardware from a given design, okay, and that is what is called design space exploration. So, so this design space exploration you can actually automate, you can actually write some script which will add those pragmas like unroll, pipeline, those things in your code and just run it and then see this give you the results, and then you manually compare which is good, which is bad and all, right. So, you can actually develop a tool for that, but most of the time people actually do it manually, right. And if you look into the code again, since I just talked about 3 levels of loops, it's unroll, you can actually unroll the innermost loop, the middle loop or the outer loop also, right. So, and every scenario it will actually give you a different hardware, or you can actually think of pipelining the inner loop and say You can apply pipeline in every stage, but usually pipeline works better when you actually apply in the innermost loop, right. And also you can actually apply the pipeline at the topmost loop, middle level loop, and so on. You can actually unroll the innermost and then you pipeline the middle one. So there are so many possibilities you can understand here, and you can actually partition the arrays. You just think of those things which can actually give you the performance benefit, right. So doing this all things is basically, there are many combinations, and I strongly recommend you to do this exercise. It will actually help you to understand how this optimization features of the tool actually help impact in the hardware, right. So that something is doable, but then is it something that I am able to achieve the best performance, or is there any coding because of the some part of the code it's actually prevent me to create a good hardware. So what I am trying to say that I apply pipeline, but I am not getting pipeline initiation interval is 1, right. So you know in the context of pipelining, if you have say a 4 stage pipeline, so my II is the how frequent I can give the inputs, right. So if I my initiation interval is 1, that means every clock I can fed into the next iterations, right, or next input. So basically that is the maximum benefit. But if it is say there is a 4 stage pipeline and then your II is about 4, so basically the pipeline is doing nothing, right. And this happen so you won't able to get this. So this initiation interval of a pipeline circuit is 1 because of primary two things. One is the data loop carrier dependencies, right. So that means you are calculating something in iteration I, and that is going to be used in iteration say I plus 1, and say that the last operation calculate that particular things, and the first iteration first operations of this next iteration use that. So I cannot just start this until this data is ready. So this kind of that stop this it adds stall in the pipeline, right, and so your pipeline does not give you the maximum benefit, right. So and also the second thing is the memory access, and you remember I have already discussed that once you map this array, this will be mapped to block RAM in the hardware. And the one of the challenge in developing hardware is that this block RAM has a limited port, right. So at most 1 or 2 ports are there, and so whenever there is a more than 2 access to array in the loop, so it will actually create a multiple it take multiple iteration just to read those element, and that might create some problem in this getting the initiation interval of the loop is 1, and or basically get the maximum performance benefit from the pipelining. So now once you apply this, you will notice that you won't get II equal to 1 even if you apply this loop unroll and pipeline, specifically the pipeline to this loops, innermost loops, specifically the innermost loop, and it says that I am not able to generate the II equal to 1 because of this reason. So it will give you some reasons, right. So then you have to look into the code, what causes the problem, right, what creates the obstacle for me to get the best hardware, right. And let us now look into the code, because I talked about that I am going to apply this pipeline in the innermost loop, because that gives me the benefit maximum benefit, and there are two problems here. Okay. So let me try to explain that. The first problem is you have 4 memory access, right. So I am accessing this in here, in here, in here, and in here, 4 memory access, but they are actually from 2 locations, right. This both this and this is actually the same memory locations, right, and this also from same memory location. So although there are 4 memory access, we are reading actually 2 element. Now the question is, does the high level synthesis compiler understand this? Can it actually understand, oh, this are not 4 reads, these are 2 reads? Unfortunately, most of the compiler won't, because there are this operation happening in different basic block, right. So let me try to explain. So this is the condition, right. So this condition is this, say. So there some reading is happening. So this read will happen here, right. This read will this in 1 and in 2 will happen here, and then this condition will be calculated here, and based on the condition you will go here. This is this if block, this is this, and else you are going to do this, right. So this part is going to happen here. So you see here this read happen in different basic blocks. This read is happening here, this read is happening here, and these 2 reads is going to happen here, right. So because these reads happen in different basic block, the compiler may not able to understand these are actually single So, these two reads of in using F1 is same, right. As a result, it may actually read 4 times from the memory, and that might create a bottleneck for this, right. So, that is something is the first problem. The second problem is there is a loop carry dependency here is also, because you do F plus plus or F2 plus plus, and that is going to use in the next iteration, right. So, in current iteration I am going to increase this index F1 or F2, and that will going to use here, but that you cannot change here, because that something is needed here, there is no other alternative. So, I cannot change that, but this I can obviously change. What I can do, I can just read this in F1 and in F2 before start of the loop using some temporary variable, and I just use it everywhere, right. So, that will solve my problem, the read. Okay. So, as I told you, this is that it is very difficult to achieve by initiation interval 1 for this example, because of this memory read, and this, as I mentioned, there are this in happening 4 times, but there are 2 different address. So, tool may not able to understand that these reads are redundant, and as a result, because of this they are actually happening in different basic block, and so it is very difficult for the tool to identify they are the same read. So, we should do some manual code restructuring here to achieve that. Okay. So, the suggestion is, I already mentioned that I am not going to read this way, I just read this in F1 and I will store in a temporary variable, I will read in F2 and store in a temporary variable T2, and everywhere instead of using this in 1 and in 2, I am going to use T1 T2, I am going to use T1 or T2. So, that solve my problem, because I do not have 4 reads. So, these simple modifications help you to achieve pipeline 1, that is a simple modification. But this is something you have to understand. Once you write this code and you apply pipeline and you are expecting that this should happening my II equal to 1, but this is not happening, and then finally you have to realize this is because of this, and just do this modification, and you should able to the initiation interval of I if I apply pipeline in this particular loop. Okay. So, that something is good. Now, the question is, does this restructuring help? Okay. Does that give you good benefit? The answer is not much, because of the 2 problems. The first problem is that most of the time this loop actually call for smaller arrays. You just remember that when you merge 2 size of 1, so this loop will actually execute only 1 time, right, or 2 times, because there are 2 elements, right. When you are actually merging size 2, it is basically iterate 4 times. Okay. And most of the time it basically has smaller arrays, because it call 8 times when the if I assume my array size is 8, this particular function will call 4 times, and every time it will just return for 2 times. Okay. So, the number of iterations is basically small, and we are calling many times for smaller arrays. Only for bigger arrays, when you are merging 4 arrays, it will be called once, right. So, because of the bigger array we have the less number of arrays, right. So, the primary problem is that although I achieve my initiation interval 1 for this loop, but this most of the time this loop will actually iterate for very less number, 1 time, 2 time, 4 time, and so on. So, this does not give you much benefit on pipelining, right. So, even if I apply pipeline, I achieve my II equal to 1, but this may not be the best design, it does not give you much performance benefit, right. And there is another problem is that, because once you apply pipeline, you have pipeline stages, and you have to flush the pipeline before you start the next iteration. And here, because I call this function often for smaller arrays, and my first call does not give any benefits, and then you need some clock to flush the data, because otherwise this pipeline will calculate something wrong, right. So, you have to flush the data, and then you have to call the next function. So, this actually adds some extra overhead of making it pipeline, although my pipeline is not giving benefits. So, this 2 points suggest that this applying pipelining to the innermost loop is not something is useful. Also, there is another problem here, this loop is actually data dependent, right, because this how many times this loop will execute is basically I3 minus I1 times, right. And so, this is an input to this particular function. So, it is basically, and if you know that high level synthesis, once the number of iteration is not known, statically known, it cannot give you any performance estimation, whether it won't say that this particular loop will take 3 cycle or 4 cycle or 5 cycle. So, you won't literally can see the benefits, right. So, it won't show you that, it just give you question mark on the minimum and maximum number of latency needed for this, because this is basically data dependent loop. Okay. So, basically we actually enumerated 3 problems. First thing is that pipeline does not help here, it create unnecessary overhead of flushing the pipeline, and third thing is the performance benefit is not visible here because the data dependent loop. Okay. So, in this case the common approach that we should be taken is to flatten the loop, right. So, into a single loop, right. So, here what I am trying to say is that I want because this loop is not so important, what about just putting this loop into this original merge sort itself, right. So, if I just go back here, so instead of calling this merge sort, I can actually take the body of the merge and I can place it here. So, that is what is basically flatten, right. So, actually this flatten is done by high level synthesis tool for perfect loops. Okay. But this is not a perfect loop because there are a lot of conditions and all. So, for this HLS tool may not able to flatten the loop. So, you should do manually flatten, right. So, that is what I did next. So, what I did it here is basically this is my merge sort, this is my merge function, and you remember that this is the merge call happening. I just try to bring this into here, right, this loop into here, and this result in to my this code. Okay. So, if you remember here, so I am just replacing the body of the merging two sorted array here, and this transform into this code. Okay. But this is very interesting, it is not only that. So, I did something more here. So, you just try to notice it. So, this is my that stage step, right. So, the array size merging, so that remain the same, but the next thing is very interesting. Here you see here the earlier the loop was going on from 0 to size, and it was increasing by width. Now, what I did, I just make it 0 to size and I am increasing by I plus plus. Earlier it was increasing this 2 times of the width, because I just take 2 array, a smaller array, I merge them and then I will go to the next block, right. So, basically you first you consider these 2 array of size width, then you consider this 2 array, right. So, my I is here, next I want to start this. So, this is my width, this is width. So, 2 into width I should modify, right. So, what I did now, I just merge, because my that loop comes here. So, this loop basically I just take this loop and I put this loop into this loop, okay, in this loop, and then what is happening here is very interesting. So, you have to make sure that we do the same thing, and this actually is huge benefit. Okay. So, what is happening here, you just see here is so basically I have to calculate this I1, I2, I3, this 3 index, and also merge this 2 array, right. So, what I did initially, I just put my initialization value. So, my F1 should be 0 and F2 is the width is 1, and I2 is the width and I3 is 2 into width. So, these are the initial value. Then I come to this loop. Okay. So, here what is happening here the merging is happening, the same code whatever is there in my here, right, just the same thing. So, this is the copy pasted here, the merging happening here, this is basically the merge, right. And because the whole thing is happening in the same array, so the idea is that you just go this way. So, you just take this every iteration, because finally you have to go through the whole array of size, and you just try to merge these 2 array, and you after having one iteration, you just check that you increase F1 or F2, and you just check whether you actually reach the next one or not, right. So, if you completed that part or not, if you have completed, you basically go to the next block. So, the next block going things is happening here, what was calculating earlier. So, basically that merging and this next block shifting things are happening in the same loop. So, basically you can understand that with this you can actually first merge these 2, then you will take these 2 array and you merge these 2, then you will take these 2 array, you can merge these 2, because all things is happening in together, right. So, you can understand the benefit that I am going to get. Earlier it was a 3 nested loop, I have now 2 nested loop, because I merged these last 2 loops into one loop. right. So, the operations of these two things into one. Okay. And the biggest thing that I can see here is this loop is now fixed size, right, and I can apply this pipeline at this level, not the innermost level. Earlier I was applying the pipeline at this level, third nested loop, but I am actually applying in the second nest loop now, right. So, and also since this loop is a fixed size is fixed for a program. So, I can actually get the all performance estimate of this. Okay. And also you can see here that memory read problem I have resolved, and everything is happening here. So, this again will achieve my pi equal to this loop pipelining initiation interval equal to 1, and this is the kind of best restructured code. Okay. So, now we have pi initiation interval to 1. So, you can understand that from the initial code how I reach to this, and this is the same merge sort. But this is something if I synthesize into hardware, you can actually compare this in results of this with the best level what I asked you earlier to do, and you compare the results. Okay. So, this is what you reach one level. After that you cannot go further, because everything is more or less control. Okay. So, now the question is it running in, because you know that complexity of merge sort is n log n, right, n is the size of the array. So, does it taking the n log n clocks, or is taking more clocks, right? Is it possible to improve the performance further, right? So, can I reach this n log n clock? So, if you run this, you will see that it will take more than n log n clocks. Okay. So, can I improve the performance further? But as I already mentioned that this code is mostly the most efficient version of the code, right. So, what next can be done? The next is the task level pipelining. So, we have already a sequential version of the code, and we make the code most efficient one, right. There is no further efficiency improvement is possible. So, the next thing is something is the parallelize the execution, right. So, that is what is the task level pipelining, and one of the most powerful, the most powerful optimization of high level synthesis. So, the idea here is, can I parallelize the execution of the loop, right. So, you can understand here but basically there are operations, the stage 1 operations, so you actually merge by 1. So, this is one thing, then you do merge by 2, then you merge by 4 and so on. So, can I do this operation merge by 1, merge by 2, merge by 4 things parallel, right. So, that is something, if you parallelize that part, then merge by 1 operations, merge by 2 operations and merge by 4 operations parallel, then it might give further benefits. Okay. And so, let us try to understand that what I can do is basically you have to create a data flow things, right. So, as I mentioned, I give the array A, and then here this merge by 1 is happening. So, basically what is happening here is, so whenever I give this, the first block will try to merge these two array into 1, this two array into 1, this two array. So, all these things are going to happen, but this block will do these operations and it will give you this array, right, where this each two elements are sorted. Okay. So, that is something if I can do, it will be great, right. And then I just store this result into some temp 0 array. Then I call this again the same function, but it will now do the merge by 2. Okay. So, that will basically take this 2 and it will create this, then it will take this 2 and it will create this 2, right. So, it is merged by 2, and then I store this result into the next temporary array, and then I am going to do the merge by 4, I store into here, and then I will do the merge by 8. So, here depends on the size because size of the array, the number of stage will depend, right. So, if I take this is for 4 stage and 16 element, if you take 32 elements, then you can actually have one more stage and so on. So, the number of stage will depend on the array size. Okay. So, this particular implementation will make me do a very interesting thing, is that now, because this is basically a data flow, you can see here is a data flow, right. And what I can do now, I can run these modules merge modules in parallel, and I can use a ping pong buffer style, right. So, I can use this ping pong. What is that? So, what I can do now, I will explain here. Okay. So, what I can do is now I can give say array A1, okay, and I will just do all these merge by 1 operations and I will create the temp 0, right. So, I will keep a 2 copy of the temp here, right. So, 2 arrays, I will just store this into this. Okay. So, the first say n iterations of n clock, it will take n1 and it will sort by the all individual elements and create that merge by 1 array into temp 0. So, this is for first n clocks, okay, n clocks. Then next n clocks. What I am going to do? I am going to take array A2, right, and this so now this merge array merge by 1, this is merged by 1, this is merged by 2, this is merged by 4, this is merged by 8 and so on, right. So, then now it will take process A1, A2 and it will do the merge by 1 and it will create resultant things, it try to store in this the other buffer, right. So, even buffer. At the same time, the second block will take this data, that first corresponding to A1 and it try to do the merge by 2, right, and it will store this things into say into this array, right. So, this means here A1 was processing, now A1 and A2 both are processing, right. So, this is next n clock, what is going to happen. So, that means after doing this, this data is already done, and after next n clock, after 2 n clocks, that sorted by 1 A will be here. Now, next consider the next n clocks. I am going to give next array A3 and it will now start the first block try to process A3 and it will do the merge by 1 and I am going to store it here, right. At the same time, this array will now take the data from the even array, right. So, it will take the data from the even array. So, it will now start storing the data A3 into here, it will now start the data from here and it will try to, and it will process this A2 now, because A1 is already processed, A2 is, it will now going to take A2 and then it will actually process this merge by 2 and it will store here. At the same time, this A1, this third block will take A1 and it will do the merge by 4, okay, and it will store here, right, A1. So, here A3, A2 and A1, 3 array is processing in parallel. So, 3 set of data is processed in parallel. Next clock you assume. So, now what is going to happen? This block will take this A1 and do the merge by 8 and it will give you the actual output, right. So, it will do processing A1. So, this particular array now it will take data from A2, because this is already done. So, this is already processed, this is already processed. So, now this will take this A2 and do merge by 4. So, A2 is also getting processed. So, this will now take data from A3, because this is already processed. So, and it will do the merge by 2 and I will at the same time I will go to the next array A4 and it will now store this A4 into this one, right. Here this A3 is there. So, now at this point you can understand that all these 4 module actually running in parallel and they are running on different set of data, right. So, and basically you can understand that. So, this is the maximum benefit and this will continue next n clock, it will now it will take A5, this will take A4, this will take A3 and this will take A2, right. So, this way things will continue. So, what is happening here? I am not able to improve the performance for one set of data, right. So, that is already I have achieved, but now I am doing a task level parallelism, right. So, different array will be processed by different blocks in parallel, right, and I can actually get a maximum benefits, okay. And this architecture will give me the best output, best performance, right, because now because it is a task level parallel pipelining is happened and I can actually get the best benefit. Now, the question is that what is the code modification I need to do to achieve this, okay. The first thing what we have to do is you remember this is the code I have modified, right, initially. This is the best efficient code I have identified. So, what we have to do, we have to put this is the task, right. So, this is the merge, that merge operation, right. So, this is the merge operation what I just talked about, this merge array. So, this should be written as a function now again, right, otherwise it tool will not understand this is individual things I am going to happen. So, I am going to first thing is that I am going to create a function out of this again. So, I am just going back to my old one, but I am going to keep all the features here. So, I will talk about the difference, okay. So, I will just create a function for that And next thing what I have to do is the next thing, so I just create a merge sort here. So, my top level function is now become basically just calling this, right, for the stage array, because I just bring out this part of the code into a function. Okay. Next thing I am doing here is, you see, is very important, that I am actually calling earlier, I am now keeping this into a different array. So, it was not temp, it is temp stage I. So, that tool understand that this is a different array, right. So, I am using actually 2 dimensional array now. So, that it understand it is not temp, it is not temp, it is temp 0, temp 1, temp 2, right. So, that is what is the difference. So, that tool can understand these are the 2 different array and they are not all writing into the same array. So, that this kind of data flow things can be created. So, I just, if you just remember with the original code, so earlier code it was just a single temp, right. I just compare here. Now, here it is temp 0, temp stage 1, right. So, this actually makes sure that these are different array and it can actually create that ping pong buffer, right, and this is for the last level. So, just to make sure that this is not, I am using temp stage, I am going to use temp basically B, because that is my final output. So, this is the second thing I have did. So, I just separate out this, and the third thing that I did is basically, earlier you see here this A was my array and it is basically copied back, right. So, that I am not doing back to copied back, rather I am actually using 2 different stage that I, so this input array is stage -1 and this is stage 0. So, that data flow is getting created. So, that this is the 3 difference from my original code. This is my original code, I just kept it here. So, here you can understand that I just, and this is my modified code. So, as I mentioned that stage things I separate out, input output I separate out. So, that temp I happen, this copies I am not doing, because I just keep it to different array. And the third thing I did is basically this modification is also there, and all this calculation is also now put into this function, right. So, this calculation is no more there here, right. So, these are all come into here. So, with all this modification, what are the things I can do? I can still pipeline this loop, because I can still pipeline my individual block, which will improve the performance. This is the fine grained pipelining, and the other thing is the coarse grained pipelining, where I actually do a task level pipelining. Okay. So, and then I basically what is happening here, I am actually unrolling this loop, right. So, this is what I am doing here, that I actually do a unroll of the top level loop, then only it will create these stages. So, if I just do this unroll, then what is going to happen, it will create these stages, right. So, this is the first unroll part will create the stage 0 merge by 1, then it will create. So, basically this is my merge by 1, and it will create temp 0, right. Here I am getting M. Then if I do the unroll, so it will do this merge by 2, and it will create temp 1, it will create this, finally it will create, it will give B, and this is merge by n by 2, right. So, this unroll I am not doing manually, right. So, ideally what is happening, to create this this structure I have to unroll the outer loop, right. So, this is what to do, but I am not going to unroll manually, I just apply the pragma unroll, it will actually unroll and it will create this structure, which is nothing but this, it will create this structure, and all this array I just separated out. So, I just apply unroll here, and also you can see here the temp is a 2 dimensional array, right. So, temp is now stage into size. So, I just do a partition. So, although this is a single array, so it is a 2 dimensional array, I just say ki you partition by dimension 1. So, that means each row will become one different array. So, that is why it is able to do this, this is temp 0, this is temp 1, this is temp 2 and so on, right. So, with all this, so what I did, I just bring this code here, I apply pipeline here, so that I can get the maximum performance benefit of this loop. I have to unroll this loop, because otherwise these stages will not be created, because if it is a rolled implement, it is the same loop, same function, but I have to create 4 copies of that loop. So, I will apply unroll here, and I also make sure that this particular temp, I just already separate them out, it is not the same array anymore, but I have to partition that array. Unless I partition the array, it will not create, because it is a 2 dimensional array, but here you can see it is a 1 dimensional array. So, so I just have to say I am going to partition in the dimension 1, so that it create different arrays, and finally I have to say that you apply HLS data flow, right. So, if I just say if you apply data flow, then only this kind of parallel execution that I just talked about will be executed, and it will basically create a ping pong buffer the way I just explained here. So, you can understand this is what is the best possible design of merge sort, right. So, if I just write this version of the code and give the high level synthesis tool, you apply data flow pragma, you partition this temp array into dimension wise, you apply unroll here, you apply pipeline here, and this will give you the best most efficient design for merge sort. Okay. So, this is what, and I will strongly recommend you just run this particular code and the base level code, right, and see what is the difference, right. And if you can also try to apply the same pragmas whatever I just talked about here in the top level code, you try to apply this unroll here, you try to apply unroll here, you try to apply pipeline here, you try to apply HLS data flow here, and you will see that you won't able to do to say I won't able to apply HLS data flow because of these dependencies, and there is no data flow things are there, right. But if you apply here, you can understand that this will give you efficient hardware. Okay. So, with this I summarize today's class, that we take an example of merge sort, and I just say step by step how a particular designer will go ahead, how either you try to apply the optimization of the tool or some manual modification of the code he will do to achieve the best most efficient design. Okay. Although I have taken the merge sort example here, the same approach should be applicable for any kind of design, right. So, you have to modify the design manually certain cases, because if certain things actually create bottleneck for applying of some optimizations, and you have to know very clearly which optimization should be applied where and what is the impact you are going to get, right. So, the same process whatever I discussed today's class going to be applied if you try to develop a efficient hardware for from a design. Okay. So, I just take all the examples from this book, and I will strongly recommend you to follow this, because this book has I think 6 or 7 such examples where it gradually shows how to get a most efficient design from a given specification C. Okay. Thank you.